Great. So our third speaker is Professor Matthias Ihme. He is a professor of mechanical engineering at Stanford University. He received his PhD also from Stanford University. And he was earlier on the faculty of the aerospace department of the University of Michigan. And his talk is entitled Guiding the Blind, Injecting Knowledge into Combustion Machine Learning.
All right, good morning, everyone. Thanks for the invitation. Really exciting. It's actually my first time here, and I'm super excited and appreciate the hospitality. What I'd like to do is I kind of want to follow the previous talks, and really the talk of this presentation is guiding the blind. So really we're talking about what is missing and what are the opportunities in machine learning. What I'd like to do is acknowledge co-authors. This is Wai-Tong Chung, Ashwin and Pushan. These are postdocs researchers that have been following or working with us here on this topic. So what I'd like to do is really start out with the basics. I think Combustion 101, we know the governing equations, and the question is, why are we sitting here if we know the equations, right? So I'm showing here the Navier-Stokes equations for multi-species reacting flows, and that's really the focus that I want to discuss here. What is there to know? And what we can really see is the equations are known, but there are several challenges, especially if you're looking for propulsion design, energy designs. We are dealing with a large range of scales and extensive chemical complexity, and of course, incomplete knowledge. Specifically, if you're looking to constitutive relations, these are parameters that enter the equations. So now, then we can essentially switch gears and really go about this topic of data sciences. And this is here a picture that I got from Jeff Dean, where he essentially recognized, or we all recognize, that there are essentially three competing effects that really help us to take advantage of the data. Most notable is we have more data available. They are gaining and increasing higher quality. We have more compute power, and this is, I think, really one main capability. The third one is that we have now tools available, analysis tools, open source libraries that really allow us to accelerate machine learning approaches. And more importantly, is we have a community. And I want to harp on this a little bit more as we go along. So really four things: data, compute power, analysis tools, and the community. And I think with this, we can make substantially larger impact on utilizing machine learning for scientific discovery. So data is not new in here and not unknown to us as a combustion or energy sciences community. I'm pulling out a whole bunch of data. These are thermodynamic property data. We have used them, or many of you have used them, for scaling regression analysis, and we have some really nice talks here in this community. This is one set of data. How can we use this? The second set of data, which I find most important or most interesting, is a scale on collection of accumulated data in the direct numerical simulation community over the last 20 years. And what you're seeing here is essentially almost a linear Moore's law scaling, where we are sitting currently on about several petabytes of data, roughly about 1,000 libraries, the US National Congress libraries. So this data is available, except it's not available because we don't have access to this. It's dispersed, it's heterogeneous, and it's really difficult to accommodate this. But in theory, you could take advantage of this, and that's really what I want to drive home here in this presentation. So if we have data, if we have the tools, what is missing? And these are essentially real three topics. Some of them came up in previous talks. We have to deal with errors. We have to deal with this black box, and I still believe that's an important thing. And the last aspect is data challenge. I want to show you three specific examples that we encountered, or many of you have encountered. First one is regression errors. If you're taking a naive machine learning tool to predict a simple example of a lid-driven cavity, left-hand side is the physics. This is a finite difference solver. Right-hand side is essentially just a pre-trained ResNet standard machine learning model. If you're not injecting any physics, any physical constraints, we're essentially seeing that we are obtaining unphysical errors. Overall, you still see some structure, but it is clear that we are missing some physics here that our naive machine learning models are not capturing. The second topic came up, I think, in the previous talk, is we have data available, and if we're using them as a black box, we can certainly see some scalability. This is here an ImageNet. I will discuss this briefly later on, where we're seeing right now, as a community effort, that there are performances that are below 3% of the accuracy. So we are essentially outperforming human characterizations. The simple question I have for you, is 3% enough if I'm building a rocket? And the answer is probably not, right? I don't want to sit on a rocket which is an uncertainty of 3% and want to go to Mars, right? So that's not my mission. So we have to think about this. And the last topic is data. I mentioned this already. I'm pulling here a database from the TNF workshop, the Turbulent Non-Premix Flame workshop. What we're seeing is there is, over the last 20 or so years, an extensive set of data collected. But what you're really seeing is, in terms of complexity, the data is fairly sparse, right? And we have to think about on how we can utilize this for some of our applications. So data sparsity, especially for engine-relevant problems, for complex geometries, we are still lacking data. We have some limited information. And this needs to be addressed as a whole within our community. So with this, let me really dive into 3 topics that I want to present here. The first one is regression error. I want to show you some attempts from our side on how we can use domain knowledge in order to overcome errors. How can we use physical information to constrain the models? The second topic is backblocks discovery, how we can actually use machine learning to our advantage and extract physical information. And the last topic is the data challenge. How can we collect more data as a community? How can we organize ourselves? And how can we accelerate the scientific discovery? So let's get started with the first topic, combustion machine learning applications, specifically on how can I use machine learning methods in order to do scientific computing flow field simulations. And again, by way of background, I'm interested in fluid flow, turbulent reacting flow simulations. And I want to get back to this rocket simulation. So the simple question that I have is, I'd like to use a machine learning method for reacting flow simulations, but I want to retain some of this predictability. So what I'm showing you here is, again, the Navier-Stokes equations. I don't want to go in detail. I just want to highlight a couple of aspects here. The first one that we're seeing is many challenges. You saw this in the previous talk. We're dealing with large chemical systems. The second challenge is the multiple scales and the chemical stiffness. So here, these are essentially all of our coupling terms, our constitutive relations. And the last problem is closure models. What I like to do here is to talk about 2 aspects as we go along in different contexts. But these are the challenges, and I think there's opportunity for us to use machine learning to specifically target certain systems. So what I have here is, again, a rocket simulation. This is in simple single injector configurations. What I like to do is to draw your attention to this color picture here. And you're seeing 2, in total 6 different colors. Each one is 1 different combustion regimes, right? So if you're naive as I am, well, I would run the most complex and the most accurate simulation for everything. But what it turns out is there's a whole bunch of equilibrium simulations where we don't need the highest fidelity of our simulation, right? So now the question is, how can I discover or recognize the different fidelities, adjust my simulation environment so that I get an efficient computational simulation, reduce the same computational cost, but at the same time retain accuracy, right? And that's the goal of this first topic. So now what we're seeing is regression is probably not the right tool for utilizing machine learning methods. We want to think about some different approaches here, right? So that's the question that I want to pose here. How can we use physical models versus data-driven approaches in collaborative environments? As I said, I would like to retain my knowledge about the Navier-Stokes equations, but I want to use this in a clever way, and I hope that a data-driven approach by utilizing machine learning in the context of a supervised learning can help us to make some contributions here. And the keyword is classification. Right? So classification is a very convenient tool where I'm using my machine learning model as a recommender in order to make a decision on which one of the models I should use. So let's see how this works. Again, this is this picture of this rocket simulation. FRC is in final rate chemistry simulation. So we're using essentially here methane chemistry and detailed methane chemistry simulations. I would believe this is the most accurate simulation given our constraints on the numerics and so on. What you're seeing here is the top is the temperature. This is the instantaneous temperature, this is the mean temperature, and if you just look into the flame lengths, where we're getting this flame length here, this is essentially a fairly extensive combustion regime. Now, if you're using another model, this is a flame-led progress variable model. For those of you not familiar with this, think about a very simple engineering model. Again, if you're a rocket designer, you use this model, you predict in flame lengths, which is half of the size, right? So now, this is a very cheap simulation, but it's certainly more accurate. What I like to do is to take benefits of both by selectively adjusting them. In terms of the configuration, we're looking here just as a side note to an TUM, the University of Munich and GOX methane rocket injector. Think about a pre-burner configuration. It's an experimental configuration where we have some data available that we can use to do some assessments. So our simulation framework or our machine learning framework is essentially in classifier. It's in supervised learning methods. And what we're doing here is we are first starting out with generating a database from binary chemistry simulations, and then we're exposing this to an error analysis. This is essentially our training methods where we're using or where we're testing different models. You're recognizing this FPV, this flamehead model. There's also an IM, an inert mixing model, a very crude model, which neglects all chemistry. And then we're really asking in which one of the regions or what are the right conditions in order to identify certain combustion zones. Then second conditions is, well, if I have this flow field simulations, I want to map this to some thermodynamic properties, some classifiers or input features. In this case, this is the set of about 6 different features. Mixer fraction progress variable, these are some scalar quantities, density, temperature, Prandtl number accounts for the subgrid scale mixing, and the gradient of C, for those of you not familiar, think about this as a mixing problem, right? So intuitive, I would say, well, if I'm using this, this makes a lot of sense. I did not provide this. It turns out we used the maximum information content, a machine learning tool, to identify the set of quantities, right? Then in the next step, I have different combustion models. In this case, we have 3 models. And think about this as a hierarchical model. In the simplest case, if I have no reaction, this inert mixing model is probably doing a fine job. As second level, I use this flamehead model, and if this fails, I'm resorting back to this binary chemistry model, right? So this is my framework. This is what I'm using as a trainer. And what I'm getting out of this is a classifier and recommendation that I can then use for my simulations. Now, in the a posteriori simulation or in the engineering applications, what I'm using is I have a simulation, I pull out the set of features, and then from this, I'm exposing this to a random forest, and ultimately what I'm getting out from this is a local selection or recommendation of a particular combustion model, right? So with this, I'm overcoming this issue of regression or extrapolation errors, and I have this nice hierarchical framework in the form of a classifier. Why are we using a random forest here? We're getting benefit from this because it's an interpretable method, so we can look into this and can get some input on this formulation, okay? A couple of words on the training for those of you interested in this. It is essentially a hierarchical model, and this allows us to bake in requirements on the accuracy. So what I have here is I have a cost assessment. So what I'm doing is I'm using quantities of interest. In this case, this is temperature and CO. So that's what we're interested in this rocket design. So I'm essentially computing the accuracy of each one of these different models with respect to my reference solution. From this, I'm pulling out an error, and then I can essentially test this against different characterizations. If I need a model of higher fidelity or a setup of higher fidelity, I retrain this entire framework to come up with another recommendation system. How does it work? These are our posteriori simulations. So we trained the system and then applied this for the same condition. On the top here, you're seeing this data-assisted simulation. This is my accuracy. So what I'm really asking is I want to have 2% accuracy in my simulation, right? If you look to this, the bottom is probably the most interesting results. These are the combustion model assignments. In order to get an accuracy within 2% of my binary chemistry simulations, I have different submodel assignments. Blue is inert mixing, and intuitively this makes sense. If I'm injecting fuel and oxidizer, there's no reactions. This is assigned with inert mixing. Then we have this yellowish color. This is a flamehead model. And what you're seeing is there's an extensive region where we actually have to use binary chemistry in order to accurately predict this combustion system. And this was quite surprising, especially in this region close to the injector, where I would have expected it's an equilibrium region. It turns out that our model is actually suggesting that we have to use a binary chemistry formulation. All right, that's all great. This is essentially a standard training system. The real question is, well, how good is this for extrapolation tasks, right? So we all know that machine learning models are good if I'm training this within my framework of operating conditions. But if I'm using conditions outside this training set, many models fail miserably. And what we have done here is we are running the same simulations with the only difference that we're increasing our mass flow rate by a factor of 3, right? So this is clearly an out-of-distribution sampling. What you're seeing here quite nicely, if you just look to this bottom figure, again, this is the combustion submodel assignment, this is the temperature. What we're finding here is our model doesn't fail. It really just says, well, my inert mixing model is not good enough. I have to use a model of higher fidelity, right? So we are essentially moving up in this hierarchy. The simulation becomes more expensive, but at the same time, it doesn't fail. And that's, I think, a good sign on how we can use classifiers in order to make decisions on combustion submodels. I have a brief summary here. I think it essentially just says the same. If we are clever about using different models so that they are suitable for certain tasks, in this case, classification, actually, we can take quite a bit of advantage of machine learning models. There's a little bit more opportunities, most notable of coming up with clever designs on introducing labeling, introducing also turbulence modeling, which I haven't addressed here in this presentation, but there is certainly more opportunities to advance this. The second topic I want to talk about is black box design. And what I was fascinated quite early on is how can we use machine learning models to discover science or physics. And I want to show you one example that leads to the system. I want to go back to our governing equations. So we have here the reacting Navier-Stokes equations. And these are terms that have to do with the turbulent chemistry interactions. I would say we have reasonable models. Some of them are empirical. But what we like to do is to see whether we can use machine learning methods in order to describe functional forms of the subgrid scale models. What I'm not interested in is coming up with a black box that tells me for a certain input in subgrid scale model is a certain output. I want to discover in functional form, and that's really interesting for engineering applications. Again, application here is high pressure conditions, so I like to live in this rocket propulsion world for several reasons. First of all, it's very exciting, and more importantly, it's a really risk-averse business. And more importantly is our knowledge about physical models, subgrid scale models, actually not well developed for this condition. Right, so here, again, we're using the same operating conditions, LOX, liquid oxygen, gaseous methane, engine operating conditions. And the simple problem that we are looking at is essentially an idealized turbulence. This is an HIT, an homogeneous isotropic turbulence, where we essentially injected some mixtures. You're seeing here the sphere of, in this case, I think this is oxygen, liquid oxygen, surrounded by a gaseous methane stream. This is in high pressure conditions. I think the temperature is about, the pressure is about 60 bars. And what I would claim is if you use any subgrid scale model, most likely that's not developed for this complex operating conditions. Right, so here we want to use this data set to construct subgrid scale models. And this is, I would say, a fairly manageable data set. So the problem is written as follows. We have in subgrid scale term, this is in Reynolds, our subgrid stress term, which is written in exact form like this. The main difference is that we don't have access to this filter term here, this Reynolds stress tensor. So now what we're looking for is we want to predict the subgrid scale stress, tau ij, SGS, as function of a set of input parameters. And right now, I have no idea on how they look like. So that's what at least I want to pretend. So I'm essentially using different information. I'm using the velocity, the filtered velocity, the gradients, and the second order derivative. And then I want to see whether our machine learning model can provide in functional form that is reasonable, that's physical, and hopefully reflect some of the physical intuition. That's the computational framework. It turns out that we're here using sparse regression methods. In the morning you heard about a Cindy framework, which is a very similar method. Here we found that the sparse regression is a little bit more robust. The model looks as follows. Remember, these are my features. These are the input vectors. I'm essentially constructing this vector x, which is essentially a set of selected functional forms. Beta, these are the coefficients. This is essentially weighting coefficients. And they have to equate, if I multiply this input vector times this weighting coefficients, they have to essentially allow me to reconstruct my subgrid scale stress tensor. Now, this is linear, but the sparse regression allows us is that I can take arbitrary functional complexities, and I essentially take, or we are here constructing a series of different combinations. D is an exponent of arbitrary order, and these are multiple products. So with this, I have, I would say, a fairly complete basis, right? This is a very exhaustive basis. Now what I like to do is, I'd like to ask the sparse regression to find a minimum set of basis functions that allow me to construct or represent my subgrid scale term. So what I'm doing here is, I'm using this minimization problem, take all of the functions, project them onto my solution F, and minimize this. This is against just regression. What I like to do is I also constrain this by this Lagrange multiplier here, by the sparsity preserving term, where I have this Lagrange multiplier, and I'm just making sure that the number of pre-coefficients are minimized. That's the framework. It's a very formal framework. And if you wouldn't know that this is machine learning, it's essentially just minimization formulation, right? So we are packaging this in machine learning models, but essentially it takes data, but we have a very established framework to utilize this. So let's see how this looks like. This is one detail here. What we're seeing is here, this is this basis set, and you're looking at this in fairly extensive basis set. It has about 15 different functional forms. By the sparse regression, we can reduce this essentially to the mean gradients, pre-multiplied with the velocity fluctuations and in grid size. And with this, we have a very compact set of formulations. So this is essentially one basis set. Once we are applying this, we're essentially getting functional forms that look like this. This is the subgrid scale stress tensor expressed in this form, applied to this symbolic regression form. You're finding the coefficients, and I would say this is essentially the key result. These are these beta coefficients. If you look at them, they are somewhere between 0.1 all the way to 0.2, but overall, we're getting some bias in, this, in the different gradient terms. If we are summing this up, it turns out that we essentially recovered, I don't know, an accident or by luck, Clark and Fertziger's gradient model, which has been developed about 20 years ago, essentially just by Taylor expansion. That's somewhat disappointing, I would say, because we discovered something which came out from fundamental analysis, but at the same time, it's very encouraging, since we learned that the simple model is actually also valid for this highly complex combustion environments of supercritical flows, right? So this is essentially one example. What I'm interested in is extending this further to more complex flow configurations, and I hope that there are more complex terms that allows us to do this. So I'm treating this as a framework. We have a proof of concept, and now we can essentially utilize this for engineering applications. Okay. With this, I want to briefly talk about the last topic. This has to do with data challenges. Remember what I mentioned before, our community has data, and we as a community have access to this data. How can we organize ourselves to take advantage of this? This is ImageNet. You have seen this in the morning. It's about 1.15 million individual pictures, right? So that's a heroic effort from this community, and I have to say, this is what machine learning made it to the stage where we are right now, right? So why is this so? What we're seeing here on the right-hand side is essentially a community effort over the last 15 years, where this community essentially advanced their machine learning models, and they are essentially thinking about foundational models in order to improve this classification task, right, to the accuracies that I mentioned before, outperforming the human recognition. This is what I like to see replicated in our community. And how can we do this? There's one example. I think many of you know this Johns Hopkins database. This is an excellent example where the community pulled together to establish a community-wide database. It turns out that this is perhaps not the right data set for our machine learning tasks, for the reason that it has only 9 discrete configurations. It's not diverse enough. We have to think about how to extend this and make this more accessible for machine learning. So with this, there is some effort that we had been thinking about. It is called BlastNet, which is essentially a community web platform of big data. The idea is that we are taking advantage of the community, the diversity of the data, and open source storage systems. Most notable, Cackle, which is an open source data storage system that essentially allows us to decentralize the data accumulation. And I want to briefly show you how this thing looks like. Currently, we have about 10 terabytes of data available to the system, and that's substantial. There are a number of flow configurations, in this case 6. Each one has different sub-configurations, and this is, again, already an indication of a community effort. We have different groups from Europe, Australia, and so on, which contributed their data, and I think this is a good starting point in the direction of using databases to inform machine learning. I want to show you one key result that came out of this, and this is diversity of data. Remember, if I have a small data set, my machine learning methods or machine learning tasks most likely will be biased. Here, utilizing diverse data sets essentially allows us to get a more heterogeneous system. These are currently all of the cases, in total 25. What I just wanted to show you here is the diversity of data. Think about each one of these color sets or color schemes is one data set. And what we like to have is cover a substantially large regime here. This is velocity. This is I think the skewness and the kurtosis of the different sets. If you were to have access to one data set, any one of this, you're typically trading machine learning methods for a very small task, right? If you're thinking about generalization, foundational models, we need this heterogeneous data set, and I think this might be here one way towards achieving this goal of foundational machine learning models. What can be done? As I said, keeping with the spirit in mind of forming a community. This is a community effort where folks can contribute. They get co-authorship on this, which I think is an important attribute. And we hope that within the next few months that we have about 100 discrete reacting and non-reacting configurations available that can then be used for machine learning tasks of different kinds. As part of this effort, we set up a community. We have machine learning tasks, tutorials, test cases available, which I think overcomes this initial barrier for perhaps some of the students on how to learn and how to utilize different machine learning tools for this applications. So with this, let me come to the summary here. What I showed you is different challenges that we are facing as a community on utilizing machine learning. I think there's a really bright future inside if we be conscious about what we as community know in terms of the physics and how we can inject this. Most notable is the challenges on uncertainty quantification, safety, and physical principles. And the previous talk addressed some of this in a very extensive way. More simply, if we can address the regression errors, the black box, and the data challenge, I think we might have a way of embracing and incorporating machine learning models, not as an academic exercise, but really for engineering decisions and advancing our community. I think that's all I have. Let me stop here and take any questions. Thank you.
Thank you.
Thank you, Matthias, for the great talk. So when you mentioned you discovered the clock model, right, and you were disappointed. Let's say you were discovering something completely different. How would you say that's not garbage?
That's not garbage?
Yeah, how would you say that something completely different from Smagoriski or Clark is not something crazy, or it's something that makes sense? How would you validate it? How would you convince yourself that that's good?
Oh, I see. Yeah, so right now this was mostly a trading process, right? And you would essentially incorporate this. What I think is the benefit of this model that I showed you here, this model is I can look at this, I can test limits. If I take the derivative, if I reduce the mesh size, I have physical understanding, right? And then I can make a decision on maybe it is garbage, right? So if it doesn't fulfill the convergence with wall models, right? So where I want to have a second order decay, then I can make some judgments. So I'd like to have this physical understanding, and then you can certainly judge garbage, right? Maybe this makes sense? Yeah.
Thank you. I really have questions just showed us about the flow visualization inside the rocket engine, that you have injection from the left-hand side and the conversion and divergent on the right-hand side. I see here this big length of the chamber. I think you have axial pressure gradient. How do you deal with the acoustic instability inside the chamber? Did you face? I see that you've solved the four Navier-Stokes equations with unsteadiness term. How do you deal with the unsteadiness term here?
If I understand your correction, if I'm using any one of these classifiers, how is my code still stable? Is this correct?
Yeah, I'm talking about, you have acoustics here, is right?
Yeah.
How do you deal with this one? This big problem, especially with the boundary conditions?
Yeah, I think that's a great question. So what I'm not doing here is I'm not localizing any model and randomly pick this, right? So there is a framework where I'm integrating or coupling the different combustion models. I didn't talk about this, but we have done some prior work on how to think about, well, if I have different combustion models of different fidelity, how do I connect them? So here I'm using essentially this machine learning model essentially only to make a recommendation on the different models. the entire framework in the CFD simulations on the combination of different models is done separately.
Okay, the second question. Is your model able to solve the solid rocket engines that you have solid fuel from the both sides, not with the injection from the left-hand side? Did you deal with solid rocket engine before? Just you now play with the liquid engine, is right?
It's a liquid. It's a liquid.
Yes.
It's not a solid. We're not talking about solid.
Yeah, you didn't try with solid, eh?
Yeah. I'm staying away from solid rocket boosters for several reasons. That's even scarier. So yeah, I'm sorry. This is a liquid gaseous injector. Yeah.
Thank you.
Matthias, thank you for this really interesting talk. I have a couple of questions. One, when you're collecting 100 data sets, how do you deal with the fidelity of this data? And do you introduce uncertainty or evaluation before?
Yeah.
The second question is, these are fantastic tools and algorithms. Maybe a little bit more pressing to apply them to large industrial systems where today it's prohibitive to actually be able to model than trying to resolve the last 2-3% in the uncertainty on rocket engines. So do you have any comment of how can we apply it to large systems much more effectively, which today is needed for decarbonization, efficiency, and so on?
Yeah. So maybe I talk about the first thing is how can you guarantee that the database has physical meaning, right? So it turns out if you look into ImageNet, there's about 10% misclassification. So if you pull out any picture, you think it's a dog, but it turns out to be, I don't know, a giraffe, right? So there is some baked in mislabeling of the systems, and that turns out that this machine learning model is able to deal with this, right? So that's a good thing. We don't need 100% accuracy in this model, right? In terms of our DNS, I think you guys told me at DNS are the ground truth, so what can there be wrong, right? So maybe that's a little bit naive, but what I'm thinking about is right now, we are mostly relying on DNS data, where we have information about the metadata, the mesh setup, so that the user could get into this database and essentially verify this, right? So we're not pulling any random database from the web. We're typically working with those contributors to make sure that the data are vetted from this case. Does this answer your first question?
To some extent, as long as the user can decide which database to use, yeah?
Yeah. The database is available, and you can choose on what data you want to have. But I think misclassification is actually not necessarily a key issue. You would like to have this as small as possible, these errors. But especially if you're going to large data sets, we're essentially doing coarse graining or downsampling to make this data accessible. And that's, I think, acceptable as long as we know what is the uncertainty in these models. I think your second question was in regard to upscaling. I'm not sure whether I fully understand what you mean.
What I'm trying to say is you're saying, I want to resolve the last 3% of uncertainty in predicting a rocket. Well, I'm saying maybe the application of these techniques is more suitable today for large industrial systems where, where 20% inaccuracy is good enough if we can get it, but it's almost impossible and prohibitive to run these. So how do we apply it for larger systems?
Yeah. So maybe if I'm thinking in terms of simulations, here this framework, this classification framework would essentially allow me to do this. If I want to upscale this, the simple idea is, well, instead of looking to 2%, well, you're asking for 20%. So if you want to do a very core simulation, for instance, you want to explore different industrial systems, well, you can construct a machine learning or a new machine learning model that is calibrated or tuned for larger errors that you're accepting as a user. With this, you're reducing the computational cost along the idea of a low-order model, and you can explore this to large-scale explorations, as long as you're aware of the errors associated with this model.
So it's the same model and it can be applied.
Yeah. So you would essentially, the only thing that you would have to change is you change this input parameter here. Or actually, I'm sorry, this input parameter here that you would have to do in threshold. You would retrain this. You get a different recommender for this, right? Which is good within the certain user requirement you have, right?
All right, thank you. I see that there are many more questions, but in the interest of time, we have to move on. So we'll take a break here. Normally 30 minutes, but we are late, so let's make it only 15. And so let's be back at 10:30, and to make things even more difficult, we will do the group picture right now. So